Well, I'm Professor Peter Challenor from the University of Exeter.
And I'm Professor Henry Wynn from the London School of Economics.
So increasingly in science and engineering and even in social science, we're starting to use complex numerical models solving differential equations, partial differential equations, to predict things in the real world. And the problem is those models aren't perfect. So this program's about what's called uncertainty quantification, which is trying to work out how we cope with the fact that one, these models themselves aren't perfect, the equations may be wrong or approximation, and also we don't know things like parameters within those models, and how do you cope with that, and how do you help people make decisions using models that are imperfect?
I mean, it's particularly important now with the risks facing the world, and like some of these models are used, for example, in climate, in epidemiology, and things which governments really have to take serious decisions, and major manufacturers have to use them to build aeroplanes, motor cars, and so it's essential that the different scientific communities, in this case statistics and applied mathematics, get together to try and settle some of the problems about uncertainty, as Peter says, for decision making and for prediction.
Interestingly, the study of numerical models has grown up separately into mathematical disciplines, applied maths and statistics. And in our program, one of the main things we're trying to do is to bring together the applied mathematicians and the statisticians to talk to each other and to come out and find out what are the best things that each does, and can we find new hybrid methods that are actually better than have been developed in either community.
I mean, I grew up in a mathematics department, first job, and it was very successful applied mathematics and also a very successful statistics group at Imperial College. But there was always this, if not tension, a lack of understanding about what the two subjects were about. And it's taken a number of years. There's been major attempts in the States at the SAMSI Institute and SIAM and various other attempts to try and finally to get the two areas together. And we're very grateful to Isaac Newton for giving us sort of last chance motel to do this, because it's and I think we're doing well. And the issue is not to compete, but to try and understand each other's disciplines. So that's almost the most important thing that this workshop's about. And typically the joke is that applied mathematicians don't know any statistics, and statisticians don't know anything about differential equations. That's not strictly true, but we need to get rid of that and start working together and build out of parallel streams out of something new and fresh. And that's what's, I mean, it's bridging that gap that is a really exciting thing, I think. Well, very wide. They range from, as I mentioned earlier, climate models, which are of deep interest to everybody, but also engineering models. In fact, there's been some successes already in the areas of reliability and quality in engineering, and statisticians talking to engineers. Major corporations like Boeing and Fiat and Renault and already use these methods. I have a list here: oil and gas industry, system biology, complicated biological systems, and we've got a wonderful project which Peter's helping to manage or look after on the heart.
Yeah, people now use mathematical models to help understand the cardiac system, and they're getting towards the point where they can use mathematical models in diagnosis and even in the operating theatre to direct surgeons on how they're going to remove scar tissue after heart attacks or similar systems. So these models are becoming increasingly used And if you're going to use them, you need to know how good they are, and that's what this program's about. It's about telling people how much trust they can put in those models, and how, one, we can make those models better, and run them fast enough that you can use them to do real-world decisions on the fly as the model's actually running.
And these models, I mean, obviously with the heart is biology, physics, mechanics, because the heart is also a mechanical object, and the engineers call it mechatronics or multiphysics. Several in these big, slow-to-run simulators, there's several different scientific disciplines already talking to each other. So the trouble is, as they talk to each other more and more, the equations get more and more complicated, and they take slower to run, and unless we can produce faster, what's called emulators of the simulators, quite hard to understand that, but faster models of the simulators, they can't be used. Certainly can't be used in surgery, and they can't be used to make important decisions about climate or vaccination when an epidemic breaks out. We need streamlined versions of these very good but rather slow to run simulators.
And these types of model are now starting to even come to the social sciences. People are starting to talk about predictive policing. Can you predict where a crime's going to happen? We had a lovely talk a couple of weeks ago about demography, predicting population change as a model, modelling people and how that they will react to things. And again, uncertainty quantification is really important on that, to know when you give a prediction, how good is that prediction and how much trust can you put in it.
I mean, I like the phrase socio-technical systems. I mean, these, if it's a widget, a gadget, that being used like a mobile phone, it's not just the instrument or the device, it's the people who go along with it. Like in air traffic control, you've got people, you've got pilots, you've got airplanes flying in the sky. These are systems which involve both machines and people, sometimes called human factors. And we hope, certainly with the heart and other things, we hope to move into areas like that as well. Actually, we were talking about this earlier, and I said what we shouldn't say is that as soon as you build a bigger computer or a bigger model, you fill it up with mathematics and science and so on, like when you open a motorway, it fills up with cars. But then we said we have to produce fast models which, for decision support, for people can use it for do real things for people and for industry. That's a big challenge. We sort of have to rein ourselves in on both sides. And then another challenge is to understand this word uncertainty. We've got a lot of words floating around at the moment, big data and machine learning and AI, for example, and uncertainty and risk, and uncertainty is one of those. I'm not sure we will succeed in pinning down its meaning, since we're quite specialised in stats and applied maths, but we'll have a try, and hopefully we'll liberate ourselves and think what uncertainty really means, particularly to people who work in decision making.
The other big challenge we have is we're bringing two mathematical communities together that think about these problems in very different ways. So the applied mathematicians think about this in terms of solving a set of partial differential equations. They like it in their hands dirty with those differential equations. They pull them apart. They find wonderful numerical schemes for solving them more efficiently, for building the uncertainty actually into the equations themselves. Whereas statisticians take a much more broad brush approach to this. So we tend to regard the models just as a black box. I don't care what happens inside. I don't care about the equations. And I look at that in an external way. And that's a very different way of looking at the problem. Now, there isn't a right way and a wrong way here, and that's one of the interesting things. What we actually want to do is to bring together two very different ways of looking at that and seeing what we can take that's best from both of those approaches and taking that forward. So one, we understand each other when we talk about these methods. Two, we might even be able to produce methods that are better than we have at the moment, just from having that conversation.
So just 2 + 2 is 5.